Okay, so let us resume our discussion on building a LSTM neural network to predict stock price. And essentially, the LSTM network will need an input of, in our example, showed you is 100 consecutive trading days for the Hang Seng Index. Then based on this 100 consecutive top Hang Seng Index, then the LSTM will make a prediction on the 101st day. Okay, so we have written a program that needs a little bit of explanation to make sure you understand every step involved in building the LSTM network and how it works. And the most important point that we need to know is what we have covered is not about the theory or the fundamental technique on how LSTM make a prediction. It involves a lot of mathematics. So in this course, we will just focus on how to make use of existing, say, software tools. Based on it, we can bypass all the complicated detail and get directly on building the network and let the tool help us to fill out all the detail and help us to do the training. But still, the more in order to understand the problem, the program, then we need to know the basic unit of a LSTM network. And an input of the LSTM network essentially is a time series, a sequence of data that have order between them. Okay. And depending on your construction, then the number of input in this time series can be determined when you construct the network. And essentially, each input in the time series will be fit into a particular unit, and this particular unit will kind of consider longer term in the previous, say, trading day, as well as at some point take a break to forget some too old information. And this kind of operation will help us make a prediction more accurately. So we have a long-term, say, previous data, as well as a shortcut, cut-off mechanism to make our memories at some point with just low short-term memory and forget older effects. But for this picture, all you need to know is the input is a sequence of data or value from the time series, and the output, if you have, say, in this example, T+1 unit, then the output will be T+1. So it should be equals to the number of input, because each input will kind of involve one computation and get you the output. So the number of input equals to the number of outputs. But when we actually look at the program, you will see that we can make a decision whether we will make use of this all the input, all the output to continue our analysis or just pick some of them. Okay, so this is what we have. This kind of unit is called, will be represented by LSTM. Okay, so you can imagine that you just rotate this picture, okay, vertically, and this is what we have is LSTM. The input is here, and then the A will be instead of horizontal in a row, then it will be a vertical in a row on the A, and then the output is the A. Okay, so this is one of the LSTM unit. And now, when we design LSTM unit for our training, what we need to decide is kind of two things. Okay, the number of input and then number of layer, and for each layer, how many such LSTM units that you will involve. Then you may ask, okay, how many layers do we really need, and how many, say, LSTM are each layer? Now, it's basically for us, try and error. Okay, try different configuration to do the training and see, okay, which configuration will give us the better result. Okay, and of course, there's some kind of mathematical reasoning on how the layer will make a better prediction, or if and whether it will slow down the training too much. But this is out of the scope of this course. Okay, so let us go to the program and see how we can develop an LSTM network to do the prediction. Okay. So as usual, we will make use of Yahoo Finance, and instead of getting the price of some particular stock, in this example, we will focus on the Hang Seng Index. And the ticker for Hang Seng Index is HSI, but you have to precede it by this cap symbol to signify that this is the index of whole stock market. Okay, so it's Hang Seng Index. We make use of the Pandas data reader, okay, to call the get data from Yahoo function, and the ticker Hang Seng Index, and this is the starting day of the trading period and the ending day of the trading period. So this trading period and the Hang Seng Index in this trading period form a time series. Okay, so the time series of the Hang Seng Index on every consecutive trading day. Okay. Now, if you get the data, basically you will get the opening Hang Seng Index, closing Hang Seng Index, and so on. And in our example, I just use close. Okay. But after doing this, okay, again, you don't need this if you run it locally, but if you run it on Colab, then you need this to, say, bypass some security measure. And now let us see what we get in the data. Essentially, you will see that you will get a table. And since we will just focus on the one of the column, which is closed, so all you see is just one column in this table, and which every row shows you the closing Hang Seng Index of that trading day, starting from January 2nd to 04. Okay. Of course, you do not have a January 1st because it is the holiday. Okay. So, and you see that the trading day is not consecutive, okay, in terms of the real, say, days, year. And there are some holiday that break in between, but anyway, this is the real consecutive trading day. And you will see that totally there are 1,300 something trading days. So out of this data, then we will use it to do the training and the testing. And if you plot the Hang Seng Index over this period, you will get the moving of the data, okay, this case. Okay, so in particular, you will see 2008. Okay, so this is a very important year that I've lost a lot of money, and then you see the Hang Seng Index drop, okay, horrible. But anyway, so this is the Hang Seng Index, and let us see how to write a program today. Okay, first, again, remember, for neural network, basically, the best way that you can make use of the power of a neural network is to make sure that the input are scaled into a number between 0 and 1. So in that case, then you can say kind of avoid, okay, super large number and then number near 0. Okay. So basically, this kind of scaling did help. And we will make use of our friend that we have shown earlier, min-max scale, okay, to do the scale. Now, to call this min-max scalar, you need to say, now, basically, you do not need to do that because if you do not set it, this is the default value that is specifying how these data are mapped to the range. Okay, and as I mentioned, the usual is mapped from 0 to 1. That is, the maximum value will be mapped to 0, and the minimum value will be the maximum value will be mapped to 1, and the minimum value will be mapped to 0, and all the value in between will be mapped linearly. Okay. But of course, in some application, you may change it, but this is not necessary for our case. So this is kind of redundant. Now, here, okay, again, is kind of something that I keep on reminding you. So remember, for the neural network input or for many of the functions that a machine learning package provide, basically the input is usually a table in which every row corresponding to the data, the value of one particular data point. Okay, and it is a table because in general, we will have more than one features for each data point. So it's not a one single value, but it's a sequence, collection of value for each of these features. So the input usually is a table. And basically, if it requires a table for this problem in which it has 10 features, it will also require a table for an input in which every data point one feature, just in our case. Okay, so when we say this table here, so what we are doing is trying to say throw away the date of the trading day. Okay, because this will confuse the training. And all we want is to get the value, okay, as a sequence of time series. Okay, but this, what we get is very easy. We can make use of the NumPy array function that will convert a table into the corresponding NumPy array. In particular, if the input has more than one column, then it will convert into a 2D NumPy array. But in our case, we have only a single column of value. So the conversion will be a one-dimensional array of numbers between 0 and 1. Okay? Now, again, this is the data. What we want is not a data, it's a table where each column is one single value. Okay, so even though essentially it's one dimension, but we need to reshape it into a two-dimension table, even though it has only one single column. Okay, so we will convert it into a two-dimensional table, but with only one single column. Okay, so here is it. Okay, sorry, it's not here. Okay, and -1 again is a kind of a signal asking the NumPy to compute the right value for you. Okay, because you can just count the height of the input data and determine the correct value here. So -1 is the way that asking the NumPy to calculate. So this is kind of the data that we based on. We call it raw data. Now, so after this free process, okay, statement, then you see that first, the real Hansen index will be transformed or mapped to a number between 0 and 1 first. Second, this is columns of value, okay? And when we do the translation, the raw data now will be a table. If you treat 2D array as a table, okay, in which every row just have one single value. Okay, so this is the first row, second row, they are all in the same column. So this is raw data. Now, this raw data, 1013 of them, all data. But we remind ourselves of the kind of the LSTM model that we need. The unit, basically, the input are just a sequence, as I told you, of 100%. I want 100 second is trading day. Now, totally, we have a whole sequence of, say, a Hansen index over 1,300 days. You will not just feed all the data into one in one shot in the LSTM. What we are going to do is to chop this long sequence of Hansen index into, okay, a kind of a moving window of 100 trading days. What do I mean? That means that so the Hansen index, say for example, so the index of 1, index 2, index 3, all the way up to index 1, 3, 4, 5, whatever. Okay, so this is the Hansen index that we got from the Yahoo Finance. Now we are going to create a training set. Now each data point in the training set will be 100 consecutive Hansen index, and then together with the prediction of the following day. So what I'm going to do is the input will be, okay. Yeah. Okay, so this is the first 100 Hansen index in my data set, raw data. And based on this, then I want the LSTM machine learning model to predict the Hansen index of I101. Okay? So this is the first data set. Now, how about the second one? The second one is I'm going to shift my window one position right, such that the starting point will be 101. Okay, and then get the following 100 Hansen index. Now, no, sorry. I2 second day, and then it's 101. Okay, just shift the window one position right and get the 100 Hansen index covered by this window, and the prediction will be the day 102. Okay, so all the way up to the last one, if I remember correctly, is what 1045. Okay, maybe different, but it's 100 and 1300 something. Okay, and then this is the previous 100 days, so it's 1, 2, 4, 6. Okay, and then the final one. Oh, sorry, I do not have the final one. So it's 1, 3, 4, 4. And this is 4, 3, and then it is 1, 3, 4, 5. Okay, so this is the training data. Now, remember, I want to feed the training data to the training model, and then we will use another array to store the prediction. So we need a X test and Y test, if you still remember. X is the training data, and then Y will be the label that suggests the answer. That remind ourselves that training data now is not a single value, but need to be a table. So it needs to be a table here. And now let us go back to our program. Okay. Now, what we are going to do first is to divide. Now, this is the whole training data set, 100 and 1030. Okay. Then what we are going to do is to chop this 100 and 1300, say, Hansen index into two parts. The earlier part will be used for creating the training data, and the remaining part will be used for the testing. Okay, so we just call, and we decide to take 60% of the Hansen index for the training, and the remaining 35% for the testing. So in order to do that, then after deciding the training size, now what I'm going to do is to get the first, 65% of the data, that is from the index 0 to the training size, as the training period. And then the remaining, say, data will be for the testing period. So in other words, that the whole data set will be chopped at the 65% point, such that the first 65% of the Hansen index will be the training period, and the remaining one will be the testing period. So we are going to use this one to create the window. Every index will be a sequence of 100 data points, just as told you. Okay. Now, earlier, when we first come to teach this course, then array program is kind of very simple. Just have a loop and then get the 100 data, put it in the array and do whatever NP or number array operation to create the necessary dimension, and then grab the Y and then we'll repeat it. shifting the window one by one. Okay, it's not that difficult. Okay, but it seems that still a little bit difficult for some of our students. So in the last few semester, that I'll just pick, okay, another tool called time series generator, doing exactly the things that we want. Instead of writing a program of our own, then we will just call this function to generate this window of data. Okay. The first 100 days, the second 100 days, and third 100 days, so on and so forth. Okay, so let us see how to call this. Okay, called time series generator. Okay, this is very commonly used because whenever you do time series analysis, okay, that most likely you can make use of it. That you just put the training period into the data point. Forget about this because there are some, say, for generality. Anyway, they need to, okay, repeat the input twice. Okay, and now the most important point is this, okay, is to specify the window size. So since I chop 100 index, let's say index together, the length is 100. Batch size, okay, I don't know. When I do not specify the batch size, then the data generated is not correct. Okay, I set the batch size. I do not know what is the best batch size, so I just put a large number greater than 100, 1,300. Okay, so this is arbitrary. You can try other batch size as long as greater than our data set. That will be okay. Okay, so this is for generating the training data, and this is for generating the testing data. They are all more or less the same format. After you do the kind of this two call function call, then and get it into the training data set, you will see that basically you will see that the training data is a table. Okay, and that the table with only one single row. Okay, it is true for both the training data set and testing data set. So what is the reason? Basically, the first index will be corresponding to the data set for the first batch. Okay, so it worked on the first batch, okay, and the training data, and then create the window. Okay, now, and batch size is 500. So in one single batch, it has already covered all the data set that I have. So if you check, okay, the structure of this train, okay, it is just a table with only one single row. That one single row is containing the result for the first batch of data. So you can imagine that for smaller batch size, okay, that with second batch and third batch, okay? But anyway, I just have only one single batch because my training, okay, can say handle the batch size later. Okay, so let us see what we get. So after the calling the time series generator, then the X train and Y train basically will be something like this. Okay, for Y train. Now, for Y train, basically, instead of a number, then this is the output. Okay, for the prediction. Okay, instead of single value, so here is a table again. So this is what the general say input output requirement give us. Okay, so this is why it's better to just ask the time series utility function to generate the correct training data for us. Okay, I mentioned. And for the training data set, basically, outer dimension, you will see that there's only one single row. But each single row contains a sequence of number, which is a two-dimensional array. Okay, so instead of the date, okay, day 1, day 2, day 3, it is a table with row 1, row 2, row 3, and it has only one single column. So this is the first 100 day, okay, and basically the 101st day will be, okay, it will be here, okay. So this is the 100th day, then the following 101 day will be 0.059. So this is 101st day, which is should be the prediction on the first data set. So you get the number here, okay? And then this for the second day, then we have the day following. So you basically you may get the hang of it very easily by just trading through the data, and then you will see what you have get. Okay. Okay, so this basically is what we have. The training data, training variable returned by the time series generation. It does contain two things. Okay, the X string and then the Y string. X string is for the time series. Okay, 100 day, second 100 day, so on and so forth. While Y string is for the prediction for next. Okay, so and the dimension will be generated correctly. Okay. Any question? Okay. Now, I would say post it as a chart. Okay. For those who have a better, say, programming background, write your own program to generate the data yourself, and then you'll have a better idea. So the difficult part is not for the sliding. The difficult part is how to do the shape to make the dimension right. Okay, so this is my experience is something like this. It's quite ignored kind of trading. Okay, that the basic logic of generating data usually is very easy to write a Python program. But finally, you get things wrong because the input dimension, okay, the input shape is not matching the requirement of the, say, tools that you want. Okay, so you need to go through the document to see what exactly the shape that you need, and then you need to add the necessary shape function to get the shape right. Okay, so my experience is the difficult skill is how to make use of the shape function to do exactly what you want. Trust me, not easy. Okay, but anyway, you have already helped by calling this function for you. For this function, then the data, the first vectors, I get the 0 in which, okay, for this, which is a table, that the first entry containing the sequence of, say, 100 sliding window, while the one index 1 will contain the prediction. Okay, and get it, and then you get what you want. Okay, now let us build the model. Now, the building of this model is very similar to the neural network model, the straightforward neural network model that we have built, okay, for recognizing the digit. Okay, the only difference is, okay, if you go back to it, is this one. So if you check the program for recognized digit, then it is kind of a not normal, say, it's not LSTM. That's what I say. Okay, so that for that it just create the part that the major point is just a neuron. Okay, and the neurons, and then you classify the activation function, so on. Okay, so this is you can check yourself. But if you want to create an LSTM network, then you are not, as I mentioned, not on the use a neuron in the network. So instead, each unit will be the LSTM unit. Okay, just like one. Okay. The LSTM unit. Okay. So you check it for the straightforward deep neural network for recognized, say, handwritten digits, that the part here is just a single neuron. Okay, but now for LSTM model, all we need is to ask it that the neuron will be replaced by a more complicated unit for LSTM, but the structure specification is the same. Okay, so first we call, of course, we need to input the sequential or the necessary library. Okay, in particular, we need this library to create the major unit of this network. Okay, that's called LSTM. Now, it is a sequential model. That means that the model will be layer by layer, as I mentioned. Okay, first we add the first layer, in which the major unit is not a usual neuron, but instead is the LSTM unit. Okay, that again, if you still remember that this add, initially we need to specify the input shape. Okay. So what is the input shape? So basically, remember the input has to be a table. Okay, so and then every row will be for one particular input. Okay. So what is the input shape? The input shape will be a table which is two dimension, okay, with one single column. That column will be the 100 data points in one single array. Okay, so it's one single column. Okay. Now, but remember, it's not but we have 100 data. If you still remember, okay, because the time series for the training will be used 100. Okay, as Hansen index to be the input for the training. So what is the input? 100 days. Okay, day 1, day 2, day 100. Okay, and that this is the input shape. Okay, so 101. Is it clear? So I need to write. Yeah. So basically, so you still remember the okay, the input will be in Hansen index 1, Hansen index 2, and Hansen index 100. Okay, so it's 100 data. Okay, so this is the input, but then we require it as a 1D array, it's 2D array. So this is the input for one single data. Okay. Now, so what we get is the 100 data, okay, in a two-dimensional array table. Okay, so this is the input shape. Now remember, add a layer. So basically, you need to specify the output of this layer. So in the example I give you is we will have only 50, layer here. Okay, so we use a 50 LSTM network and connecting the input to every of them, completely. So this is again a dense network. Okay, so now this is the first layer. Okay. So if you compare this to the output of the construction, you will see that for this layer, the output shape, the input shape is this one. I've showed you, but the output shape, how many output is 150. Okay, so let me explain why it's 150. Okay, so basically it will output totally we have 50 LSTM models. Then where is this 100 come from? If you still remember, in an LSTM, this is the 100 Hang Seng index, and each unit here will handle that particular input for the time series, and that unit will also produce an output. Okay, so if you have 100 Hang Seng index, then the whole process will construct 100H. Okay, so this is the output for this LSTM, 100%. What you may treat this as the prediction. So basically, you can either see what is the final prediction of this LSTM, so that that you will forget about all the intermediate earlier prediction and then look at the final prediction. Or it seems a little bit better for your learning is you get all the intermediate output for after every new signal in the time series get in and see how it can say make prediction. Okay, so you can have two choices at least. First, you just forget all the previous prediction output and then get the final one as the final prediction. Or you can just also use this whole 100 input output, for further training. Okay, and how to determine what you want by specifying this return sequence. Okay, I set return sequence to true here. That means that for every this LSTM, that it will not only give the last output, so say for 101st, but get all the 100 output, for each time series. So you have 100 output here, 100 output here, all the way for all the 50 LSTM model here. So totally is 150. Okay, so this is the output shape. Okay, and then you see the parameter basically is corresponding to the number of edges, more or less equal to the number of edges in each of them. Because we do not have the new structure here, so we cannot say compute why this is the case. But anyway, this is the output trace. Okay, the next we add another layer, and then we add another layer, and then we also have 15 LSTM unit, and also the return sequence is also true. Return sequence of also true. Now for it, we do not need to specify the input shape here because this input shape is connected to the output of the previous layer. So basically, it just equals to 150. Okay, but anyway, you don't need to specify. So this is for the second layer now, and now for the last layer, add another 50 LSTM network here. But remember, mind you, that in this layer, the last layer, I did not set return sequence to true. That means that each of this LSTM will be using the last output of the last day to be the prediction, while all the series, say 99 days, will be ignored. So for this one, the input shape is only 50. Output shape, is only 50. Okay. After this, then the last one is to add a dense layer that with only one single neuron here, and then connect all the output. Okay. Now, if you look back to the neural network that we construct for the feature recognition, we see that in the specified dense layer that we also need to specify the activation, say, units. Okay, the regular LU. Okay, but for this, okay, if you not specify it, that means that you will not have any activation function. Just get away from, and that will be output. Okay, so this is getting the weight sum and get the output, and this weight sum and the output will be the prediction of the 120. Okay, and now for the compound, as I mentioned, that the accuracy is a safe function that do not have second derivative, so it is not a smooth curve. So the general, say, calculus technique cannot be applied. So basically, we use another substitute function, the error function. Okay, so that we, based on it, we can know how to minimize it. Okay, we do not know exactly how to minimize the or maximize the accuracy and minimize the error. Okay, but now if we define more, say, manageable function, then we can ask to minimize this one. And this time the optimizer is called the atom optimizer. Okay, there are many of them. Okay, but this one basically is kind of the jack of all trades. Basically, whatever problem, if you do not have any idea of what the particular optimizer that are most suitable for you, then we usually use atom. Okay, at least this is one. Our research basically will always call atom, and the result is not that bad. Okay, so this, okay, after that, then you have all these results here. Okay. Now, so up to this point, we have, say, specified the basic architecture of the LSTM model. Okay. Now, you can now train it by feeding the training data and for X, the testing data set, and then the label. Okay, and also you can specify the validation data set yourself. Okay, so basically, if you see, you can always compare. Okay, that the statement here with the corresponding statement in our, say, previous feed-forward model. Then you see that they do not specify the validation data set. Okay. And I suppose they will do it for you, but anyway, this will provide your own validation data set. Okay, and in my testing here, I try 100 approach. Okay, that means that you repeatedly redo the training 100 times. The batch size will be 64. That means that I will not use all the, say, 1,000 and something, say, data set, but instead every time you just use 64, okay, and then do the run the atom optimizer to minimize the error on this 64 data point. Okay, after that we will feed in another, say, 64 data point, and then do the optimization. Okay, that in this training, second time we will forget about the first batch of data point and focus on this 64, get a new network, focus on the foreign 64 network, repeat it until all the data, okay, has been complete. Okay, so this is one. Verbose basically, you can try to say 0, then if try 0, then you will not see the intermediate, say, result. Okay, so this is what we have. Okay, and then you do the training. And I will leave it to you to run the program yourself on Colab. Okay, it's very straightforward. Okay. Any questions? Okay. So now, basically, we have gone through the building of the model as well as fitting in the data to do the training. Okay, so after that, then we have a model, then we can just use the model to do the prediction. So we have, for example, you can call the model predict, that is the usual function that you use to do the prediction. And then I'm trying to do, okay, two prediction here. The first is the self prediction that use the training data set to see how well the model can make the prediction on this training data set. Okay. And then we will, okay, make the prediction on the testing data set. Then this one is kind of, it's not a waste of time to make the prediction on the training data set, because this say prediction, when you compare it to the model, then you have some idea on whether the training is overfitted. So if you see that the result is very good, 99% correct, then most likely your model is overfitted. It's not just worth it. Okay, but anyway, this is what we have. So we have the prediction here. So of course we can compare the result. Okay. Now, one more step is remember what we are working really is not the real Hansen index, because at the very beginning we have all the min-max scalar to scale the real Hansen index to a number between 0 and 1. Okay, then looking at this 0 and 1, okay, output may not be that user friendly. So you need to convert it back to the original index, Hansen index, okay, according to the say transformation formula. You need to remember it. You can just call, okay, the scalar inverse transform to transform all the numbers 0 and 1 to the corresponding Hansen index. So you need to call the inverse transform for the testing of training data set, the prediction for the training data set, and then for the prediction for the testing data set. Okay, so this is the training prediction, and this is the testing prediction. Okay. Also the code. Okay, that's it. Okay, so you have the data. So now let us move ahead a little bit further. So in the say the program, the final program part here is to kind of show the prediction on the diagram, then you have a better idea on how well the prediction will give you. Okay, so forget about this first. Basically, remember the blue line is the actual, say, stock price or Hansen index over this trading period. Basically, we have two kinds of prediction: the prediction for the training data set and the prediction for the testing data set. And if you still remember, for the training data set, basically it's from the whole period of Hansen data, we chop the first 65%. Okay, that is early part to the training data set. So the prediction will be at the early data part. So this is the prediction of the model for the training data period. Okay, and this one is for the prediction for the testing period. Okay. Now, if you just look at the prediction, basically you will find that our model is doing better for the training data set. While for the prediction, well, it's not that accurate. Okay, but I think it should be fair to say that the testing data set, the period here is kind of chaotic, okay, for the market. Okay, so this is not that surprising that they did not have the necessary data for the training in order to say make good predictions of this chaotic series. But anyway, this is the result. Okay, and this is focused on the testing data only, and then draw the real Hang Seng Index together with the prediction. Still, you see that is kind of a little bit lacking. Okay, so in this point, it's dropped already to this point, but it's still okay. I predict that it is rising. So a little bit lacking on the prediction. Okay, so now, okay, before we take a break, let us see how to draw this curve or draw this curve. Okay, this is not that difficult. Any questions? Good. Okay, now we are now not working on machine training, but we are working on drawing a curve. Okay. And for drawing a curve, then we will get back to the normal NumPy 1D array. So we don't need to reshape it into 2D, but in fact, we are working in 1D array, which will get the X data point and the Y data point, and then we draw it on the picture. Okay, so now in order to do that, we need to have some kind of container to contain the data point for drawing. Okay, so for this data point, you remember what is the value of this data point, what is the value of foreign data point. So we want to have a NumPy array to store the Hang Seng Index over this period. Okay. And also at the same NumPy arrays have the Hang Seng Index for the prediction of this testing period. So we want to have a large NumPy array. So each entry will contain one data point. Okay, and this data point will now can be used to plot it and get a very nice looking diagram here. Okay, so what we need is to create a NumPy array that stores the correct prediction on the correct day. Okay, so here we will just create an empty NumPy array. Okay, and basically, the size will be equal to the raw data, 1060. Okay, but anyway, this has nothing to do with the actual value, but it just use it to create a NumPy array that is where the shape is exactly the same as the data. Okay, so because this is the real data, the real Hang Seng Index. And I just want to, on top of it, print the data with the same shape. So we just create an empty array that have the structure similar to the original data point. So this is what the intention. Okay, and then we just initialize it to some initial nonsense value, or not a number. Okay, to make sure that it will not cause any error when we plot the graph, that if we do not specify any value to it, it may cause the plugin get into some trouble. So we just first initialize it to this value called NAM. Now, okay, so now let us see what the prediction. Now, if you look at it from here to here, is the first 65% of the Hang Seng Index period. And now we will chop this period into windows of 100. What is the first prediction? The first prediction is not day 1, it's not day 2. Okay, it's not day 100. Because the first 100 will be the first window for the training. So the first prediction will be 101. So that means that the prediction that you call basically is not for day 1, day 2, okay, but starting from day 101. So the prediction that you got from the machine learning basically is starting from this point. Okay, it's not, so the first 100 days will be empty. So this is why you it's good to set all the points NAM first, because now you don't need to worry about the value of the first 100 entry, because the plot function will understand how to handle NAM function, namely ignore it. So it will ignore that part, okay, and then we will copy the prediction, okay, not starting from day 1, but starting from day 101, because this is the first prediction date. Okay? So this is why what we're doing. So the prediction basically starting look back is 100, not from 1 or not from 0, but start from 100. Okay, so the data point 0, 1, 2, 3, all the way up to 99 is the first 100 Hang Seng Index. So the index 100 will be the index for the 101st day. So this is the starting point. Then this is to the end of the training prediction. But then for this training prediction, now you see for the training prediction here, okay, so if this is the last window, if the last window will be start on this day, then what is it as? It's not from that beginning of that window, but from that window you add another 100 to the end of this window, and then the prediction will be the day following this window. So the ending will not, okay, from the training predict the last day, but we will move to another 100. So this is corresponding to the right position for putting the training data. Okay, so this is the training prediction. Okay. And similarly, you can just for the testing data again, instead of starting from the end, so basically is instead of adding 100, you see you add 200, because 100 is the say window shift by the first prediction, but then after that you start from here, you basically the first 100 data will not be the prediction, but the next 101 will be the prediction. So the difference now is not just add 100, but add 200 for the shifting. Okay, so this is why we add 200 here for the shifting. Okay, maybe it is too tedious here. Okay, but I just it's worth your effort to just look at the setting of the at 100 and starting point here in order to say get a better idea on why we set the number array in this way. Okay, the major reason is that we have kind of using first 100 Hansen index to be the first testing data set. Okay, so the first prediction will be 101. So this is we need to shift. Okay, and the other will have the similar reason. Okay, so after that, then basically you can just call PLT to plot the data. Okay, the first one, okay, is the data that in fact you don't need to call data here because we have raw data. But anyway, we do the transformation to this is for plotting the real Hansen index over the period, and this is plotting the prediction for the testing period, and this for plotting the prediction for the training period, and then you show this one, you get the data here. And you can just kind of focus on the testing data, okay, and then print the result, and then you have a final diagram to show the prediction here. Okay, even though you look at it, it seems that the prediction line is acceptably close, similar to the real data, but anyway, the prediction here is not good. Okay, because there's a lot of points that if you follow the prediction, you will lost a lot of means. Okay, any question? Okay, so this will finish our discussion on using our STM model to do stock price prediction. And I can tell you that this LSTM model is kind of the hot topic 4 or 5 years ago. And now we have other more recent kind of agree, usually universally agree that they are better than the LSTM model for time series. Just Google and you will get a lot of this kind of information. So it's also a possible type of career project. Okay, that kind of do similar say prediction, but trying to make use of earlier some latest techniques. Okay, for paper there's a lot of them. Okay, but I still have not come across with say very popular software platform that provide the implementation of those kind of new network technology. But anyway, if you say get the data, usually the author will say put their program on GitHub. Okay, that's a lot of popular trend. Okay, but still you can try them in order to get some idea, and maybe you can try it if you want to experiment for your course. It's also a good idea. Okay, so that's all for this one. Let's take a 5 minutes break. So let's get back to 25. Okay, 25. What I should return the first 2 variables about the first match. Yeah. What's about the second? Now, this generates basically is generally the data for the first window, for the second window, and then for the last window. Okay. Yeah. So this will be 0, 1 for this whole part. Okay. So basically, this is an array or list of lists. And then in this list, the first entry 0. Basically, it has 2 entries. Let's do first, right? S1, which is another list. 1 is another list containing the windows of the Hansen index. And then the 1 will be the prediction for the T101, the T103. So it's another list.
So it's tracking by the program.
Yeah, well, it is the program that generates. But of course, if you like you write your own program, then you have a different ways to generate them. It's not that difficult.
It's difficult, right? I found that the skill operators doesn't do since
You want
in format.
Yeah.
Thank you. Okay. 我哋即係我哋 project 咧，因為我哋卡嗰個嘅十啱用唔錯啦。
哦，你唔止一個啦，好多個問題，一於去。
係咁，我哋都諗住組隊試下。我問好多錢，都80幾萬，係咪
哇，犀利啊！咁唔使你，就玩下啦，玩下翻下啫，
即係佢好簡單啫。佢就攞 nest 最後尾個10分鐘。每10秒為一個 interval，
佢就係
咁咁咧，嗱佢就3:50開始，去到4點就係10分鐘，就3點即係00秒開始啦，10秒、20秒咁佢，但係咧一開始嘅時候有200支股票㗎嘛，係，咁佢10秒之後咧，呢200支股票即係佢有個方法計一個屬於嗰間股票裏面啲 bid ask 嗰啲嘢啦，你當下佢叫蛙嘅呢啲嘢，每一隻股票有隻佢自己嘅蛙，你有200隻股票咧就有200隻蛙，喺 initial start 定3:50過10秒之後咧，佢又會 update 啦，有個新嘅蛙，我哋就要去估，就係根據你讀晒咁多日嘅10秒、10秒、10秒，然之後你就去估佢個例，可能話係 end day 嘅一開始嘅嗰10分鐘咁。即係我想問喺咁嘅情況之下，因為我哋平時上嗰啲咧，其實都係舉個例子咁，我哋講聽日截幾多，或者後日截幾多，即係你係升高波，佢而家係200隻咁樣行咧，我哋應該
嗱呢啲下去即係點講啊？去考慮啲 machine 同埋考慮啲 server efficient 嗰點哇睇點分嘅200咩咁啫，即係 high frequency。
佢個 wall 咧就10萬個。
係要自己 develop 嘅。
係啊，
我諗都要。
唔係我哋自己條 team 咧就諗住咧就一開始先寫咗60秒就唔好上10秒太 high feed， 就諗住用60秒先。係咁，但係有咩方向我哋可以
冇啦，俾我嚟，我淨係識用 CPD 咁快啲就。
唔係我唔需要快，但係起碼 run 動先啦。即有冇啲咩方向咁？即係例如我見上網其實啲人咧都係用啲咩 XGBoost 啊，嗰啲乜boost 嗰啲即 extreme gradients 啊嘛。咁你一個啦，另一個就 RNN 啦，另一個就 LSTM， 即係咁。但係問題係即個方向係咪啱咧？咁
嗱 LSTM 方向就肯定冇錯啦，因為佢都 performance 咧都公認係 time series 咧，佢係。唔係最好，但係一個 reasonable 嘅。咁但係你用咩 data train 嘅？
佢俾咗你，
即係我意思係個 train 可能
好耐，而且1個鐘一日。
佢哋無限玩嗰啲玩成幾日啊！有啲 GPU 翻嗰啲爭嗰啲咧，佢哋玩幾日咋佢哋。所以我真係唔知啊！我玩嗰啲都係啲細路仔嘅問題咯，呢啲真係大人嘢，我真係唔好識啊！
唔係，我哋都要交到個 project 先 ，set 咗個 project 先再搞其他嘢。即係你明唔明？即係我哋起碼都要報到個 project。我見啲人其實 po 出嚟嗰啲都唔諗去攞獎嘅。
咁啊，
或者係咁講，你用佢個 data set，你其實好難。
唔係我知係用佢嘅 data set，
可唔可以抄出嚟？唔得，唔可以用。
佢俾你抄嘅，佢 convert 咗啦嘛。
哦，
佢 convert 咗啦嘛，佢已經講到明，佢 convert 咗俾你嘅。即係佢 convert 咗，好似 convert 咗0.1咁樣，你唔會知道佢個例可能個 identifier stop picker 係0.68，咁你唔會知佢咧 Apple 定邊隻噶嘛。
哦，總之係一紮嘢俾你。
我知一紮嘢俾你噶嘛。
唔知啊，嗱，我真係
即係 LSTM
我淨係做嗰啲 research informatics 呢啲咁嘅 finance 嗰啲嘢咧，其實我諗冇係真係嗰度浸成幾年咧，你真係好難知道點樣。冇所謂，
但我哋未必 run 到一個滿意嘅結果，即係個 project 嚟講，即係你明我意思，即係我哋可以 explore 嗰樣嘢，之後話俾你聽，我哋 explore 啲乜嘢，但係可能最後尾我哋乜 Q 都 explore 到，即係
你講咯，冇人知道個 result 係實得㗎，做 research 唔會大。
即係我哋都係不停 Google，不停 check GPT 問你點做嘅啫，即係唔係？我哋都要攞。
我而家 check GPT 你使唔使俾錢？
要俾錢，你俾咗錢之後咧，每一個鐘定每3個鐘可以問20條，你可以調整到 Excel 翻俾佢，叫佢 generate 出嚟啦。但問題我哋要有個思路啊。
唔係，我意思係，而家我哋啲學生可以唔出 GPT， 唔知 MSc 學生俾唔俾嘅？
冇關係。
知啊，你而家用自己錢啊嘛。
係。
咁如果 department 俾錢，你就唔使用自己錢啦。
都少錢啫，我哋啲 part time 出嚟翻工，你一個月先得嗰唔知100-200蚊港紙，大佬。
我知。
你100零蚊即係你飲少幾杯咖啡都有。
我唔係要問啊，因為有人有學生問我，咁佢哋係咪有啲 function 係貴嘅？佢問個 ChatGPT 可唔可以 department support 啊嘛？咁我話嗰啲錢你冇都用。
咪係有嘅，話唔知可以唔知問20個問題嘅，鬼事。我大佬你咁少，我自己又問 ChatGPT 都問過百條啦，你咁樣搞，你得個20條，咁啊打暈都唔夠啦。
咁啊，而家有 ChatGPT 我乜都越嚟越鈍啊陰公，我寫啲 report 嗰度，咁你大佬真係我唔使諗啫，我中意即係個學或者咁講啊，都一個好嘅 skill 嚟嘅，因為我哋知道我哋考 report 入邊有啲咩 major point，咁但係中間好多廢柴嗰啲嘢咧，你唔寫落去咧又唔似嘅，但係咧你要寫嘅時候好嘥時間，而家我懟咗佢，眨下眼就。
好啊，咁我哋再 explore 下，即係除咗 LSTM 嘅，仲有冇多1-2個推薦下，可以 explore 下俾我哋起碼嘅方向。唔係，我哋都係細路仔嚟嘅啫，係咯。呢個嘢真係好嬌勁嘅，因為佢真係 hedge fund 嚟，佢真係就係做 hedge fund，我哋都唔識嘅大佬。我哋唔係好犀利嗰啲人啫。
問下 ChatGPT
我問咗啦，佢俾咗幾多塊，一個就 RNN，一個就 LSTM，一個咧就
RNN 好耐噶咯噃。
咁係方向啫，即咁我都要個 project。
唉，真係啊！
我問咗，我知嘅。
唔係啊！好鬼衰啊！同 ChatGPT 都要 preset 咧呢啲嘢，啫。即係唔識點樣呢個參書咧，我唔識呢個。邊個啊？參書多咗。
呢個 proposal
喂，我哋呢啲唔係啊，我呢啲揾個笨嘅。
咁就呢個係3點free version，你知唔知我買個 server VPN 就已經可以用咁多條，都買20條啦，仲要唔係4點咯，你叫佢廿招啦。
有啊，我有啲咩 reference 㗎。
OK，
好，再嚟一次，又要我再打。 呢個真係先知佢 LSTM GRU 係啦，GRU 係 GRU 係啊係，呢個係真係好用嘅。呢真係有用㗎，呢個好嘢嚟㗎，呢個 Temporal Convolution Network。我嗰次去睇一個我哋MT 學生去做個 professional talk， 佢係用呢個嚟做time series 嘅。佢其實咧，佢哋會 combine 呢一個 with GRU 嘅，做好多得意嘅嘢。你可以睇下啦，你抄埋啦，唔好嘥啦。N-bit 真係好快啲，係咯係咯。就唔使先生嗰啲啊。
我其實咧，即係好老實講，你將條曲咧貼咗落去，我叫佢 explain 條面拉埋拉，佢講得好無理佢真因為佢真係磨下個問題，佢又唔會嫌你煩，咁你叫佢逐行佢哋
我用咗呢樣，我發覺咧，篇下文章真係一大抄。佢係因為佢喺 Google 嗰度咧，或者嗰啲人走晒啲嘢咯，佢求其揾啲啱嘅抄底俾你啦。
但係你叫佢 explain 啲曲，你叫佢抄嘢，我記得。呢個我唔記得。
好，咁我至少幫咗你。
That's true. Yeah, I have a question. You know, the structure of STM is this, right?
No. It's like this. And okay, it's A evolution of the A. Okay, so this whole thing is LSTM.
This is one narrow.
Yeah, like LSTM. But then the input are the whole time series. T1, T2, T3.
So,
Yeah, right, exactly.
And the time information is from this to this.
Yeah. No. Independent. So this is the input, the T1, T2, T3. The information is from here. And then this is the output, X0, X1, XT. And then this is kind of the prediction. Okay.
So, in each loop, the information updates itself and has nothing to do with the neural net street.
No. Yeah. They are independent. Okay, but you will connect to the next layer.
Okay. Thank you.
Yeah.
Okay. Okay. So it's during the break. So one of you comes to me. So we are talking about PM and then which we that and then other data models that unfortunately is going back for PM. And then he asked me one day. I told him I don't know. I'll check GPT mode. So we use the ChatGPT. Okay, immediately there's a long list of say the latest say neural network configuration. Basically, this is okay. So I think a few years later, and you may not you but the student may think that why they want to spend so much money to take an MSc courses, just use ChatGPT, okay, to learn all the latest needs and all. Anyway, okay, so now let us move on to the latest another new technology which is called reinforcement learning. And kind of 5 or 6 years ago, reinforcement learning become kind of a very hot topic because Google has a deep learning that developed an AlphaGo that beat the human master or playing Go and that kind of thing. So basically, their technology is based on a new concept called reinforcement learning. And the major advantage of using reinforcement learning is as a developer, we don't need to prepare the data for the supervised learning. Instead, the model itself will adjust and get the learning themselves. Okay, so this is called reinforcement learning. And here is a basic idea on
Sir, your mic slows down. We can't hear you.
Oh, okay. No, the mic is kind of not working.
Can you hear me?
Okay, good. Okay, so before we get into more detail among reinforcement learning, there's some general setting that we need to lay down. The first is the major player in reinforcement learning experiment is called an agent. You can imagine that it is a robot that we want it to learn how to solve problems or playing game. Okay, race is a skill. Okay, so it's okay. Okay, so you want the agent, which it's a program or it's a real robot or whatever that run a program that you want it to say change its internal circuitry or program data structure such that it will change its behavior to some say direction that is desirable for our real user. Okay, so this is what the main objective is, to train a system we call an agent. This system may be a real robot or maybe a program or whatever. Okay. Now, in order to do the training, we need to provide a so-called environment. And this is another program. This program basically will perform the following tasks. So whenever the agent takes a step, then the environment will decide whether the step is good or not. If it is good, then it will decide how to, we will give the agent some reward in order to encourage, its behavior in this direction. And if the action is not good, then it will kind of punish the agent. Usually it's just by reducing the amount of money that it has, in order to make it understand that this action should be avoided. Okay. After that, then the agent will decide what is his next move, and then each move will change some condition of the environment we call the state of environment. So this is the two major player in the reinforcement learning framework. We change a system called agent. It will work in an environment which will give it reward when its action is good and punish it if its action is not correct. Okay, and then each environment will also react to the agent's action and thus change its state. Okay, so basically this kind of so the success of a reinforcement learning application depending on both things: whether the agent is intelligent and its capability to learn, and also equally important is the environment that it can correctly decide whether the action taken by the agent are good or not. Okay, and then decide the right amount of award or punishment in order to kind of direct the agent to some better opportunity to improve its behavior. Okay, and basically this is what we have. And when we describe a reinforcement learning application, there are some say general terminology that I don't want to go through it, but they're just listed there. Okay, you see that I'm not written it myself. I just copy it from OpenAI. Okay, that is just give a very kind of official definition of the term that is reinforcement learning. Okay, the environment, the state of the environment, the agents that you want to train, the action of the agent. Okay, for every step, that means that whenever the agent has get a new state from the environment, that it will take another action, such an action after finishing it just corresponding to a new step. Okay, and the reward given by the environment and also the penalty, the punishment. Okay, now we have a target, so this is kind of not that clear, okay, because different application will have different target. In our case, that our target is to train a robot for trading, and the target, of course, is to make the best, largest profit. Okay, but for other things, example, then the target may be playing a game to win a game and so on. Okay, the target, the policy, it is the kind of the guide map that the agent will follow in order to say improve its behavior. Okay. Now, an episode, basically, you can imagine that this is running again. Initially, there is an initial state, and that I will go through a lot of steps, interaction between the agent and the environment, and eventually, the playing will eventually reach its target or its threat. Okay. After that, this will one episode. Okay. So this is what we have. Now, why we episode? Because in the learning, you will see that when you want to train an agent, usually you need to run many episodes, because initially the agent is not that intelligent, so it will fail pretty soon in, say, within 10 steps. But after one episode, you can imagine that it will update its internal state such that when it plays the game again, it will have a better initial state such that in that episode it can run longer. And run longer means that it will set its internal policy a little bit better, and we have a new episode. So you can imagine that if you have enough time, then running the episode more and more will give you a better performance. Okay, so this is the general belief. Okay, now, and here basically is just to give a kind of a universally used adopted diagram, okay, to explain the reinforcement learning, say, explain it. So basically, this agent will run some reinforcement learning algorithm that it will say get the new state of the environment. Okay, sometimes we call observe the state of the current state of the environment, and based on the state, it will run the algorithm will decide to take an action, and this action will kind of forward to the environment, and the environment will check what this action, whether it is a good action or not. Based on this action, it will change its internal state, and then it will kind of tell the reinforcement learning algorithm whether its action will get a reward or a punishment, and how the amount of them. Based on this, it will change its state and so on. Okay. Now, here, we need to run a program. that have two entities. One is the environment and one is the agent. And usually we will kind of imagine that what we need is the agent. Okay, but no, not only the agent, the environment itself is also very important. If you can design a good environment, it will definitely help the learning process of the agent. Now, as the matter of fact, since the training, the learning rate for reinforcement learning is not that efficient because it is not unlike the supervised learning, you cannot give a very clear, say, indication on what is the correct action that it will take so that it can learn it. It will gradually, okay, learn from the reward and punishment that it gets. So it will be a very slow process. So the environment, for example, we are able to develop a reinforcement learning application on, say, through algorithmic trading. Okay. That you use the real environment. Basically, it's hopeless. What do I mean? So if you really wait for the real environment to let the agent to decide whether the position is a long trading position and short trading position, but then it need to say wait another day in order to see whether its prediction is correct on the other day. So basically, this kind of real environment is too inefficient for you to do the training. Okay, so basically, the research on the community, okay, and that's some sponsored or supported by, say, large, say, organization, okay, will try to help to promote the research of reinforcement learning. They write simulation program for the environment, and they spend a lot of research effort to provide, okay, simulation programs that will make sure that it will be, say, give the right reward and then can determine more or less correctly the determinants of the action of the agent, whether it is good or not. Okay, so what I'm going to say is that, for example, for us, in order to, say, develop a reinforcement learning algorithm for algorithmic trading, we need to have an environment for stock, okay, trading. And we don't have, okay, we can't, okay, use the real stock market result in order to use it as the environment. Okay, but basically, fortunately, OpenAI and other similar large organizations spend effort that you provide a lot of different simulation programs for different environments. Okay, and in particular, for stock trading, later we will see a particular environment provided by OpenAI. Okay, now, so basically, this kind of environment is not human, but it makes a great contribution to the advance and the development of reinforcement learning. In particular, okay, so we'll see that the researcher in the field, basically, they still face the problem is they don't have, okay, cannot use the real environment to test or train their algorithm for reinforcement learning. Okay, and more importantly, of course, they can write their own simulation, okay, program to simulate the environment. But this kind of writing their own simulation program for the environment can have a very important problem, namely that different researchers, okay, they propose a new algorithm, and when they test it, they use their own developed environment to test their program, okay, and then they can also use their own environment to test the performance of other reinforcement learning, okay, algorithm, okay, in order to eventually say that my new algorithm is much better than the other. But if you using, okay, your own environment, then no matter how good your result is, people will take your result with some pinch of salt. They don't trust it, okay, because they are depending on different environments. So basically, in the initial stage of the research of reinforcement learning, okay, we get into the same problem. We don't have a common yardstick to compare different reinforcement learning algorithm proposals, okay, because we don't have an environment, okay, that everyone will use it to compare. And to use it, we have to make sure that the environment is a good environment. You work well on the bad environment, eventually when you come out, it will not give you it. Okay, so fortunately, okay, OpenAI, okay, is still Elon Musk support this organization, and that is spend a lot of effort to develop different best environment so that any researcher want to propose some new environment, they can new algorithm, they can use the environment to convince the other guys that the performance is good. Okay, so this is the environment. So what this I think that before you talking about reinforcement learning outcome, we need to talk about environment. And basically, there's other new say environment that you can get. Okay, of course, ChatGPT can tell you. But anyway, this is one of the most famous environment that most of us used 1 or 2 years ago. Is from OpenAI. Okay, the name is called GYM. Okay, that provide a lot of simulating environment. This is some background information about OpenAI, and ChatGPT is also from OpenAI. And then, so this is the GYM. GYM is a Python library developed and maintained by OpenAI, and it provides a lot of standard environment. Okay, and then you can check it and see the environment. In particular, that is one of the page that you will see. One environment is to play the Atari game, okay, which is called the Space Invader. That is in my generation, okay, 1980s. Okay, so when I was a teenager, we used to spend a lot of time to play this as a student game. And so basically, now they provide this environment, and then you can write your own reinforcement learning algorithm to learn how to play this game to say a very skillful level. Okay, so there's also other environment. Okay, now in order to let me try it.
We are going to work on an environment that from OpenAI that called Carpo, that we just showed you a basic step that we will use. So let me see. Okay. Okay. Yeah. Anyway, because I want to show how this can display the movement of the Carpo, but I need to set up some. Anyway, we go back to the Colab and then run the program, and then you avoid this problem. But anyway, sorry about the delay. So let us go back to. Okay. So now I'm going to describe an example that is provided by the it's called Carpo. And the basic setup will be like this. Okay, it's a very simple game. That it is the this is the horizontal line, the basket. Okay, and then you have a cut here, and on the cut on top of the cut there's a code that is initially is vertical position. Okay, and then at the beginning, then it will kind of a random force will push the card either to the left or to the right. And after this push, then of course the vertical pole will lose its balance, and then it will try to fall. So if you put it to the left, then the pole will kind of incline to the right, and then try to kind of falling on the right. Okay, in that case, the agent basically need to learn what it should do if we know that, okay, the card is moving to the right and the pole is kind of falling on the left. So in that case, you will imagine that the agents will try to push the card to the right in order to make the card of the pole, okay, regain its upright position. Now, the amount of force that it also will need to learn, because if say pushing too hard, then the Carpo will automatically falling from the right position to the right position, will falling to the left position. So that is a lot of decisions need to be made in order to make the Carpo. What is the target? Okay, the target basically is you write a
agent in which it will learn how to balance the card flow such that every time they make a push, it will most likely to rebalance the card flow. Okay. So in the last 2 semesters, but not for this semester, but the last 2 semesters, okay, I have given in the assignment asking the student to develop a card flow program in order to try to balance this card flow using this OpenAI environment, and the grade will be depending on the number of steps that the student's program can achieve. Okay, so initially I would expect that the result will be kind of around 100 or 200. Okay, and it will be very good. Okay, but eventually, okay, many of the students are so smart, they're much smarter than me. Okay, they just go to the Google and find existing advice reinforcement learning algorithm, cause it to this problem. So eventually, many of the students use a program that the number of steps that they can achieve this kind of kind of nearly 1 million. So it's kind of crazy. Okay. So now for this semester, I will not make the same mistake. Okay. So, but anyway, it's kind of a very interesting exercise. Okay, and it's in a matter of fact, come across with a student that basically its algorithm is very simple. Push right, push right, push right, push right. Okay, but surprisingly, it can achieve a few thousand steps. Well, of course, if you say take a random step, that is every step you flip the coin and it is ahead and push left, it will tell it's right. In that case, that it will give you really bad performance. Usually, it will say cannot survive more than 10 steps. Okay, so after describing this environment, even though I will not ask you to do it in the assignment this year, but anyway, you can write your own program, try to write some program that can beat the 1 million mark. Okay. Okay. Now, in order to now I'm going to describe this card flow program, okay, environment to you. Basically, the action that the agent can take basically is very simple. The action can be 0, which means that it will push the card to the left, and 1 push the card to the right. Okay, so basically you don't need to worry about the false amount of the force. Okay, it's keep you a fixed amount of force every step. All you need to decide is whether you push it to the left, to the right. Okay, so the algorithm that the student gave me I told you earlier is 0, 1, 0, 1, 0, 1. Okay, so this is the amount you get. Now, but of course, the decision of whether you push the card to left to right, you need some, say, information about the environment. And in this example, what information the environment will give you. And basically, if it gives you the card position, card velocity, okay, and then the pulse angle as well as the whole angular velocity. Okay. Now the position, of course, is not infinite. So the horizontal line, the position here is minus 4.8, and the position here is 4.8. Initially, the card will be at position 0. Okay, and also it has a velocity. Initially, it is a 0 velocity, but if you keep pushing the card in one direction every time you push it, of course, the velocity will increase. Okay, this it just say that it is not have any limit on the velocity. In general, it's not, you will not be too large. Because if it is large, then very easily you will push it out of the line. Okay? And then this angle, pole angle of the pole basically is minus 44 and 22 degrees. What does it mean? So basically, this pole are allowed to stay in a fan of 24 degrees to the right and 20 degrees to the left. It's minus 24 degrees and positive 24 degrees. So what does it mean? It means that if you play the game in until it stays that the pole's angle is greater than 24% of angle, and that or minus 24 degrees, not 4 degrees, that it will you have no chance to say continue, and then it falls to the ground, and the game stop if the pole angle is say falling out of this range. Okay, so this is the say termination condition, that if your pole angle will falling out of this max and mean range, then it will stop and you flat. Okay, another of course is the angular velocity, no limit. Okay, so you can imagine that when this start, a random force will push the car, and then the speed and the position of the cars will change, as well as the angle of the pole, as well as the angular velocity will change. Okay. After this change, then you can say check any of the condition or all of the conditions. Based on it, you decide what you do next. Either push it to the left, push it to the right. Okay, so this is what we have. Now, here is an example, okay, that will make use of this environment. So let me, okay. So in order to do that, because this will be a very simple example that it will take a random action. So we need to import the random library to get a random number. Okay, but the important point is, okay, this set. It just import the GYM environment, okay, from OpenAI. Okay, and in this library, there's a lot of environment that you can use. In particular, I'm going to use in this program is called the environment cat home. It has two versions, V0, V1. Okay, and I'm using V1. Okay, and this is the environment name. So I just call the library Jim and ask him to make an environment for me, and the environment is Kafka version 1. So after that, then okay, I will get a new environment which is okay referred by this variable A and B. So every time I can make change to the environment by referring E and B. Okay. So now, after setting this environment, so this is the main part of the program, which will say work at forward. We first call the environment that I've just made and call the function reset to reset the environment to its initial state. Okay, I'll try to delete it. It worked perfectly well. Okay, but anyway, this is one of the say recommended step is reset the environment. Okay, and then we keep on. Our goal is to make the code say upward for as many steps as possible. So after each step, then I will increase the number of steps to see how many steps that I can maintain. Okay, so now we will enter an infinite loop that will continue, okay, to the following. Get a random number between 0 and 1. The 0 for left, 1 for right. So it's just a random action. And based on this action that I have to declare, then I can call the environment function stack, and with the argument is the action of the stack. And this, after this step, the environment will give, okay, the program a new state. And the state, as I mentioned, is this for observation. So basically, it will give you the state, which is for observation, together with the reward done input. Okay, so this done, basically, it will be true if, okay, the type falling out of the boundary of the horizontal line or the pole fall outside the 24-degree bound. Okay, so whenever it is false, that means that you can still continue playing the game. But if we done to true, that you must stop because the game is over. Okay, so you just continue doing it whenever it is done. Okay, it's going to fall. Okay, so all you need is to work on this part. But if you check this environment to revolve basically, okay, it gives you no particular useful information. It just always be 1. Why 1? Because if you survive this step, then you have a 1. Okay, but so every time you still survive, then this 1. So it will not help you too much about making the decision. So the most important, say, information that you get is the state. And if you check it, the state is just a list contains the 4 numbers here. Okay. Now, after each step, it is to survive and include the number of steps. So maybe you can write a program yourself and then see this random, say, action agent. So how well it performs. Okay, I'll try it myself, and this will only survive for about less than 20%. Less 20 steps. Okay. Now, so of course, you will not take random action for every step. Okay. So now, there's a lot, many reinforcement learning algorithms. That depending on very clever dealing idea. One, but however, for any course in machine learning, talking about reinforcement learning algorithm, that one of the must teach Dino is called Q-learning. Okay, because it is kind of the most simple or kind of among all the existing reinforcement learning algorithm. This Q-learning is among the simplest and most intuitive algorithm. Okay, that we can use of. So let us go through this Q-learning method in order to give you some idea on how, okay, to do reinforcement learning correctly. And now, this is what most of textbook that you will see. Q-learning is based on Bellman's principle of optimality. Anyway, let's skip this. Not important. Okay, so what is the idea? Now, basically, we want to keep a table, quality table, such that this table will give us, okay, some suggestion on what to do, okay, based on some state that we have. And we will assume that in applying this skill learning, the state is not continuous. Okay, so the couple basically is no use in general. Okay, because it is the state is a continuous number. Okay. But still, later you will see that we can still apply pure learning idea to couple is simply by applying the idea of binning. Okay, basically it is to chop the variable into different groups so that we will need to handle a fixed number of groups instead of a continuous number. Okay, but anyway, we will decide or kind of modify our problem in such a way that we can describe the state of the environment by finite different group of state. Okay, and then the action, usually the action is split and filled in number. Okay, so now I'm going to see, I try to maintain a data structure which is a table such that it has classified by the state and the action. So you can imagine that for the couple, say for example, you go to a table such that it has two columns. Okay, one column is for pushing the couple to the left, 0, and then one pushing the couple to the right, and then the row will be corresponding to different state. Okay, suppose we have to do the binning so that the state now is kind of divided into different groups, and there's a finite number of small number of groups to them. So every state, and then every day we have to actually. Okay, so this QSA basically will tell, if it is good, it will tell us that if after a step, then you observe from the environment a new state S, that based on this state, you have two choices, whether it is pushing to the left or pushing to the right. So what is the decision? Basically, if you look at this table, quality table, and then you compare the quality of these two actions under this state. Okay, so in this row, look at the 0 column, 0, 1. If 0, 1 has the largest value, that means that this action has a better quality or a better potential for you to, say, balance the couple factor. So basically, you just look at this quality table. Now, if you are given the best quality table, for this, say, couple problem, say, for example, then the life is very easy. Basically, every time you get a new state, and then you look at the row, corresponding row, and find the entry 0 and entry 1, which one is largest potential, then take that action. Okay, so this is not the problem. The problem is how to get the best table. So you may imagine that initially this table contains some garbage. Nothing reasonable, just a random number. And then you can imagine that after every step, then you will make some educated guess on the value, of some entry, and then it will make change in order to make the table become more useful in the future application of the step. Okay, so what we need is to figure out how to update the table or the learning part is to update the table after every step, such that after enough steps, the table will become good enough for you to say make a good choice after every step. Okay, so how to learn? Some high-level idea. So suppose you are in the state S, okay, and by looking at the output, you decide that you take an action A, okay, and then after this one, then of course you go tell the environment, and finally you can see that the result you get is it brings you to a state S. So this is the information you get. Okay, so now let us see how that we should update the Q table for us. Suppose in general we have k possible action A1 to AK. So then now we have already completed this step. You can do nothing about it, but then once you move to S pi, the new state, then you need to take the next action, which can be A1, A2, and AK. So which one? Now here we will not look at the table first, and then and basically we will kind of so maybe I use it. So now I'm talking about Q learning. So now we have the Q table here. And now we are in state S prime. And then we have action A1, A2, AK. So according to the idea is, since each of the Q table entry will tell us the potential of that action that will balance the pole. So in order to make the right choice, then basically I will choose the A pi among AK, such that Q A pi, S pi, A pi is among the maximum of all the possible actions. So this is obvious because each entry will tell us the potential or the value of taking that action. In order to get the best possible chance of balance the card pool, say for example, then we go through all the entry, pick the one that gives us the largest entry, and then just choose that action. So this is obvious. Now, this is what we have. Okay. So let me summarize what we have. So we have encountered a state S. Okay. And then we have taken action A. After taking action A, then we come to a state as I. Okay. So here. Now after that, we need to update the Q table. But now we look at one step further. So QA is the initial, quality estimate that we have. But now, after taking one more action move, we put into this new state. Okay, that new stage also is the Q table's current estimation on how good our position is in this state. Okay, so if we compare these two, that means that QSA is the current step that we take, and it is a suggestion on how good this action is for this state. And after taking the right action according to the principle of optimality, we move to the next stage, with Q pi and A pi. And that entry also suggests, after this action, how well our situation is to get a better position. Now, just imagine that, we want to update the QSA. And now, after one more step, we move to another situation. We have QS pi A pi, that action. And that table, QS pi A pi, also suggests how good our position is. So basically, this if QSA, and after taking the action, we get a better position. That means that basically we can just take this and then have a better chance to increase our chance of survive longer. So what does it mean? So you compare these two values, the original QSA, and then what are the chance, prospect after taking one more action. If we find that after taking one more action, our prospect is better than the original estimate when we are QSA, that means that the QSA is not that bad. Because if I take the action, one step further, we will come to a state that will suggest that we have a better chance to survive longer. Now, let me repeat, it's time. So now we have a Q table. And then from the Q table, the action that we need is we take, in the current state and take action A. Now, this is exactly what I'm going to take according to the general principle. I will take this action. Then after taking this action, then I will go to the next step is QS pi and A pi. Now, this is the new situation that we reach. And if that new situation tell me that, okay, our prospect, its estimation of our prospect of the game is better than QSA. And QSA will bring us to this stage. So that means that QSA is not that bad because it should be as good as QS pi A pi. Because when I'm a QSA, take the action, will go to QS pi A pi, and then it will, okay, from that move on to play the game. If QS pi A pi suggests that we have a better chance than suggested by QSA, but still QSA start from there. So that means that QSA is even better than estimate, okay? Because after one more step, okay, we have a better chance to win. So of course, before that step, okay, and then the chance start from there, we have better chance to win. So that means that if this is QS pi A pi is greater than QSA, then that means that the original estimate of QSA quality is not, okay, that bad. So we can improve it somewhat. Okay, so I don't know whether I can kind of convey my idea correctly, but this is the idea. That means that after taking one more step and then reach a situation is even better than what it predict, okay, in the previous step, then of course, okay, I can have a better chance to win, okay, even on previous step. So I need to increase the quality. On the other hand, if QSA tell me that, okay, I have, say, 90% of good chance, okay, so I'm very happy that according to the standard mechanism, I know that I will be moved to S pi and A pi, but after this one move, it say that I'm going to lose, okay? So basically, in that case, that means that the original suggestion is not good, okay? Because taking this action will bring us to a falling situation, okay? So basically, this suggestion is no good, okay? I should reduce the quality, okay? Because after one step, when I look at a little bit further and then find that I will be trapped into a dangerous situation. So of course, I should update the original QSA to say avoid this situation. So in other words, even though it's kind of not that clear here, the idea will be very simple. The QSA now suggests what is, okay, the quality of this action. This is a guess. Okay, now I decide to, okay, move forward according to this action and bring me to a new state, okay, and then and the action that I will take. Now, based on this new state and new action and compare with QSA, if the new state and new action will suggest a better chance of winning, then of course our QSA current estimation should be better. On the other hand, after this new step and then we bring it a situation that is very bad, then of course the current estimate of QSA will not be correct, because even if I believe it, that it brings me to that situation, then of course I need to reduce the cost, the value of QSA. Okay, so this is qualitatively suggests, okay, how to update the QSA. Basically, either increase it or decrease it. Okay, and the idea on whether we should increase it or decrease it is execute one more step, look further, and see what the new situation tells us. If we have this, okay, bring us some better situation, then I increase QSA. If after this, okay, this step bring us a worse situation, then I reduce the QSA. Okay, so this is but the problem is, okay, how much that we need to make the changes. Okay, now this is the magic formula from Q-learning. Okay, what is the magic formula? Remember, we are talking about adjustment of QSA. Okay, so as how to do the adjustment? Of course, from the current value, and then this part is adjustment. Okay. Now, as I mentioned, this adjustment is positive if, okay, this action brings us to the new stage, okay, that is better than, okay, better than the current state. So of course, I can increase QSA. So if this is positive, okay, then I will make the increase. If it is negative, then I should make the okay. Sorry, there's a typo here. Okay, so this will be our parentheses. Okay, so basically it's the difference, okay, to make the changes. But there is some adjustment that that the designer or developer need to decide. Okay, there's a one discount factor. That means that how important you say the difference will affect the change. Okay, so if it is say large number, that means that the difference will be very significant. That will make you change. Okay, quite significantly. Okay. And so, but of course, you will decide that whether you want this different. Okay, how much effect it will make the change of your rate. Okay. Not just the difference, but you get this count factor here. Okay, usually it's smaller than 1. And also, we want to make use of the reward, not for couple, but anyway, in general, we want to take account into the reward in order to say help you to make the adjustment. Okay, a little bit back because if the reward is good, that means that the environment also decided that your move, like this one, is also good. So this will also should be considered, okay, and the factor to increasing the current Q value. And also, this is the learning rate. Is this kind of, if you imagine that everything is random, okay, then this is not that meaningful. Okay, so basically, if you do not want to make dramatic change because you know that initially you are working on something not that meaningful. So you expect that the improvement will be accordingly a small step because you don't want initial, say, randomness take over and mess up all the possible real learning. So you have a learning rate such that if the rate is large, that means that the factor here will kind of make a significant change every step. But this is give you a risk situation that it will not lead you and convert to some, say, stable Q value. Okay, and so this is the general formula. So what can I tell you is that experience of this Q learning find that by setting the right alpha and right gamma, basically is kind of very effective for many courses. Okay, so the reason is being that it's kind of every step will make the adjustment. If every time, may not every step will give you the right improvement, but once you can set the improvement correctly, that it will be there. It is kind of if you do not set the learning rate too much, that any real improvement that it will kind of stay there, and then it should kind of keep on improving. And the real reason is basically is the principle of optimality that I just avoid. But the main reason that is every time we are not say take action randomly. We kind of every time we will get the best action suggested by the quality table. So if the quality table indeed will give us the correct prediction, then the action that we take will also be improved. And that means that the value will keep on improving and bring us nearer to the best possible prediction. Okay? So this formula basically is the usual, say, formula for this, QRAM. Okay, now, here is give you an example on using Q learning to play the card code. And now, basically, we'll go through the program. But basically, I just want you to at least today explain how to solve the problem of the continuous value. So remember, the Q that I'm using Q value, that means that the state should be discrete. And as a matter of fact, it should be better that the state is not too many. Okay, so the table will not be too large, and we have better chance to learn the right Q table quicker. Okay, but now in our example of this problem here, then the state are continuous. Okay, the couple, the cut velocity, angle, and so on, they are real numbers. Okay, so but this is kind of a very commonly encountered problem because we usually need to say handle value as if they are a discrete group. So we are using the technique called discretization of the value, or put it in a more direct way is to kind of use beam to group the value together into one single group. Basically, we can imagine that the state will be very critical for us to make the correct decision. But for a couple, say for a couple with angle 24, not 24, maybe a couple with 5 degrees and a couple with 5.1 degree, basically it will not make much a difference between these two situations. So what I'm going to say is, even though the value are continuous, but the difference from two very close value basically will not affect the decision very much. Okay, so in other words, it is kind of not necessary to distinguish a degree of, say, 5 degrees and 5.1 degree. So what we are going to do is to divide the fan. If you remember, it's minus 24 degrees all the way up to 24 degrees. Falling all of them will be end of the game. But then this continuous value of 24 degrees to minus 24 degrees to 24 degrees, we just cut it into how many of that? 6, okay? So it's 16. Okay. So 24, 24, okay, about 8. Okay, so some number. Okay, so we just divide this fan into 6 different smaller fans, such that now we have only 6 states on any degree falling into one particular scenario fan, and we have that. Okay, so this is kind of a very commonly used technique to convert, say, a continuous value into, some category. Okay, so this is what we have. Now, we will explain this program. Okay, it's not simple, but maybe it's kind of simple. If you look at it, it's all the assignment thing. But we need to go through it one by one. So maybe we stop here and then we will talk about this program in the coming class. Okay, so that's all for today.